Swayam Prabha. Digital India. Educated India.
Okay, so in this lecture, I will be talking about design of packet bed height. So far we looked at material balance problems where for a target separation, we find out the optimal liquid flow rates or optimal gas flow rates in the case of stripping. Okay, and the second aspect is we looked at the calculation of pressure drop for a packet bed. Through these pressure drop calculations, we also calculated the design diameter for the packet bed. Okay, so using material balance, desired flow rates are specified. This includes the calculating of minimum flow rates. Second is we used fluid mechanics principles in order to calculate the column diameter. So we looked at a lot of issues regarding column diameter calculations. So we want to ensure that the column operates below flooding line so that the operation is stable. And subsequently, if you look at this material balance problems, usually we have an equilibrium line and then we would have a operating line, and from the operating line the slope is proportional to the flow rates ratios L by G. Okay, so this is Y2, this is X2, this point is Y1 and this point is X1. So when we do this material balance, we calculate the desired flow rates. What we have implicitly assumed in this process is that the packet bed column has a sufficient height to achieve this particular mass transfer operation. Okay, so there's an implicit assumption that was made. But now we are going to ask that question. Suppose if I know the flow rates and the inlet outlet composition, to achieve this particular material balance, what should be the packet bed height? Okay, so this will involve the mass transfer rates or mass transfer operation itself. Okay, so using mass transfer principles, we are going to answer this question. So once we achieve this particular target of calculating the packet bed column height, we complete the entire design of packet bed. Okay, we know how to calculate the flow rates, we know how to calculate the diameter, and we know how to calculate the packing height, and that completes the design of absorption column. Next to this, there will be energy cost and economical analysis that will not be part of this course. Okay, so now when we do this absorption column height calculation, this problem can be split into two parts. One that deals with dilute mixture, another one that deals with concentrated mixture. Why we do this? Because if you deal with the dilute mixture, we will see that this calculation can be done analytically with a pen and paper. When you go to more concentrated situation, such analytical solution may not be possible. We have to resort to numerical or graphical method. Okay, so we'll go from the very easy calculation to more complex situation. So our problem will be split into dilute mixtures. This we will do first now, and then after that we will discuss the concentrated mixture problems. So here analytical solution is possible. That means we'll have a formula, we can plug in the details and then we can get the column height Z. Okay, so this is an analytical formula. Whereas in the case of concentrated mixture, we will use either graphical approach or numerical approach to calculate Z. Now let us look at why the dilute mixture case is so simple to deal with. So when I say dilute mixture, I am talking about both gases as well as a liquid. Okay, so in the entire operation, if you look at the change in the compositions both in the liquid or in the gas, you can treat both mixtures as dilute mixtures. Okay, so the consequence of this assumption is the following. First of all, the molar flow rates that is G and L, they will remain almost constant. So you don't have to deal with this solute free basis for these calculations. Okay, so the mass transfer, the compositions are so low, they are very dilute, that if you look at the variation in the molar flow rates of the gas or the liquid, they are almost a constant. So we can treat them as constant. So you don't have to have G1 and G2 and so and so, you can actually treat them all G. Similarly, you don't have to deal with L1 or L2, you can call all of them as just L. So this is one advantage of, or one manifestation of this dilute mixture assumption. The second is to deal with the equilibrium line. The equilibrium line can be conveniently expressed using Henry's law, where H is the Henry's constant. And this is also a very fair assumption as long as you are looking at dilute mixtures. And the third manifestation is that the mass transfer coefficients F and K, they are equal. Okay, so F type is something that we use generally for a concentrated mixture, K type something that we use for dilute mixtures. So when you look at this absorption like problem where a single solute is transferring in the non-diffusing solvent, so A diffusing through non-diffusing B, kind of a mass transfer type, you will see that for dilute case, F type and K type are analogous. Okay, this was something I demonstrated in one of the previous classes on mass transfer, interface mass transfer, but we can also see it here. So let's say if you have a F type mass transfer coefficient, you generally write the mass transfer rate as 1 minus yi by 1 minus y. Okay, so here we are talking about a two-phase mass transfer like this. So this is an interface, this is y, and you can have yi here. So this is x, and you can have xi here, right? So here this is the mass transfer rate for A diffusing through non-diffusing B with the F type coefficients. So now when the compositions are very dilute, we can actually approximate these logarithmic terms. If you expand this around 1, you will see this is roughly yi, and ln of 1 minus y will become roughly minus y, and if you substitute this, you get y minus yi, and this is actually equal to how we write K types mass transfer coefficient. Okay, so because of this relation, we can use F type and K type coefficients interchangeably as long as you are dealing with dilute mixtures. Okay, so these are the three advantages that we have by assuming dilute mixtures. 1, the gas and liquid flow rates are nearly constant. 2, we can fairly use the Henry's law to describe the equilibrium line, and third, the F type and K type mass transfer coefficient can be interchangeably used. Okay, so these are the consequences. So with this, now let us go to the actual design. We are talking about a packet bed. So gas goes at the bottom, leaves at the top, liquid enters at the top, and then leaves at the bottom. Now we have looked at these kind of diagrams when we did this material balance, but now we are going to do mass transfer operations, and we have to recognize that this particular column is actually packed with a packing material. And this packing material we have discussed before could be rashing ring, it could be interlac solids, it could be burl saddle, and so on. So, okay. So what I have shown here as a hatched region, so this is basically a packing. It can be a random packing or structured packing. And another thing you have to remember is that in this kind of a packet column, the contact between the liquid and gas is continuous. Okay, all along this column height, the liquid and gases are constantly in contact with each other. Okay, so we have to deal with this as a continuous contact equipment. So packet column is a continuous contact equipment. Now take a particular section in this particular column with a height equal to dz. Okay. So this would be G at Z, and this would be G at Z plus delta Z. Similarly, the liquid is coming here, L at Z plus dZ, and L is leaving at Z. You must be familiar with this shell balance when we do the design of when we do a material balance, or when we develop a material balance for a continuous contact. So we are trying to do something very similar. We are taking a very thin section of a length dz, and this would have a cross sectional area A. Okay, A is the cross section area of the column. So now let's write the material balance here for this particular thin section. So we have G A Y entering at so what I have done here is I am looking at the difference between the moles that is leaving Z plus delta Z minus the gas that is entering at Z. That should be the difference. The difference between these two should be the net mass transferred. Okay, you may recall G is the in the units of moles per unit area time. Okay, the units of G is so many moles per unit area per unit time. So here this area refers to the area of the cross section without the package, without the packing. So if you think about this column having a hollow structure, you calculate the area. This G is with respect to the cross section area of the column A. So moles per area per unit time. So that's G. When you multiply this with the area A, then you get moles per time. When you multiply that with the mole fraction of solute Y, you are basically talking about how many moles of solute A is leaving the system at location Z plus delta Z, and the same quantity that is entering here. So, this is the net change in the total moles of solute A in the gas phase, and that should be equal to the mass transfer rate. When I look at the mass transfer rate, I put a minus sign because I know that for the gas phase, it's absorption problem. So, the solute is transferring from the gas phase to the liquid phase. So, it is going to be a negative sign because it's losing. And here, with respect to the mass transfer rate, I've written this flux. Na is a flux. This will be also in moles per unit area per time. However, this area is not same as the cross section area. This area corresponds to the interfacial area available in this particular thin shell. Remember, this column has a packing material so as to give gas liquid contact area. We have to account for that particular area. So, this area is different from these areas. Okay. In terms of flow rates are defined with respect to the cross sectional area, whereas the mass transfer flux is defined with respect to the interfacial area, and the interfacial area is a characteristic of the packing material. Okay. That is why I have used ds to denote the available. So, ds, this is the available interfacial area in the volume A times dz. What is A times dz? A times dz is nothing but the small thin volume that I have shown here in this red block. Okay. So, I am looking at a particular height dz and it has a cross section area of A. So, the volume of that section would be A times dz. In that I have a packing, and I am asking how much area, interfacial area, is available for the mass transfer in that particular section. So, now I can write this ds is equal to some A times A dz, where A is a property of the or characteristic of the packing material, and this is given in the units of meter square per meter cube. So, A is a property of the packing material. It is given as the area available per unit volume of the packing. Okay. So, let me reiterate again. We are talking about two different areas here. One area is a cross sectional area of the column in the absence of a packing. That area is used to define the molar flux of the fluids, gases and liquids. So, when I write the mass balance, I write GAY so that I know how many moles of solute is going through this column at this particular section. Okay. Whereas, when I look at the mass transfer rate, I am looking at how much mass transfer is occurring in the chosen region. In this case, the mass flux is with respect to the available interfacial area offered by the packing material. Suppose if I do not have the packing, I can use the same A here also, but I do have a packing, and the mass transfer should be calculated with respect to those interfacial area. Now, to calculate this interfacial area, we have to recognize that this interfacial area is a very strong function of the packing material. Just like in the calculation of pressure drop, we define a flow parameter F for different packing. Similarly, in the same table, if you see, the interfacial area is also given. If I go back to one of these previous classes, yes, which I kind of asked you to ignore before, now I am going to ask you to pay attention to. So, if you look at this table, you see that I have cut down some, I have struck down some of the details. Those are the interfacial areas. So, use the same table to calculate, to find out the F factor, at the same time the packing interfacial area. All the things that you see in the bracket here are the interfacial area. They are given in the units of so much meter square per meter cube of the packing. So, coming back to this here. So ds is the available interfacial area in the volume A dz, because that's the volume that I am taking into account, and that ds is written as small a times A dz. Small a is the interfacial area per unit volume of the packing, and this has to be multiplied by the volume of the packing, which is A times dz. Meter square per that should be feet square by feet cube, I think. Yeah, because that's in English unit. You can check. I think it should be foot squared by foot cube, something like that. Yeah. Sorry, whole table was in English units, is it? Could be, yeah. But doesn't matter because in this case, this is independent of the units. This is a simple mass balance we are writing. Here the units do not really enter, whether it's SI unit or English unit, both should be okay. Okay, but when you use this table to get the A, you have to make sure that you are using consistent units. Maybe you have to change it in terms of SI units. Okay, so we will now substitute this expression. So we have G A Y at z plus delta z dz minus G A Y at z. This is minus N A small a capital A and then dz. Okay. Now I can cancel all the areas that are common here. So I would have Gy and I am going to bring this dz here. So now in the limit of dz going to 0, I can approximate this as the derivative of Gy, and that is equal to minus Na. This kind of a balance is something you do for plug flow reactors in terms of chemical reaction engineering. When you do a kind of very similar operation where you will write the shell balance in this way. So there's a lot of analogy to this. So now at this point, to move forward, now we have to define what Na is. Okay, for absorption we can use Kx y minus Yi. Okay, so Yi is the interfacial concentration, in terms of mole fraction, and Kx is the local gas phase mass transfer coefficient, MTC. And we already saw that we can replace with an overall coefficient capital K, sorry, this should be K. I thought somebody will actually point this out. So it will be Ky. Okay. So now I am going to use the overall coefficient, and what should be the driving force? Yeah, what is the driving force for overall mass transfer coefficient? Y minus Y star, right? For those who find this difficult, so what we are talking about here is, so Y is here, this is Yi, okay, or we can use the Y star here. When you use this driving force, use the overall coefficient Ky. If you use this driving force, you use the local coefficient. Okay. All right. So now let's substitute that here. I already mentioned that the flow rates are so less that the G can be kept constant. Okay, so I can take the G out of this integral. and then separating the variables. So I can separate the variable and I can integrate from 0 to z, that is from the lowest to the high top, from the bottom to the top of the column, and the corresponding composition should be from y1 to y2. Okay. Now I can absorb this sign minus by changing the limits of the integral. So I can write g y2 to y1 dy by y minus y star, and that is z. So this equation basically tells us how to calculate the height of the packet column. So what are the information we need for this? We need to know what is the gas flow rate G. We need to know what is the overall gas phase mass transfer coefficient. We also need what is the interfacial area offered by the packing material, and then the limits of the integration, that is the composition at the bottom, at the top, and this y minus y star. This y minus y star is basically the driving force available for mass transfer across y1 to y2. Okay. So if you recall, we have the equilibrium line, and then the operating line is somewhere here. Let's say this is y2, this is y1. Now as you go from y1 to y2, you look at the driving force. These are the driving force lines, and this integral is basically integral of 1 by the driving force. Okay. So now this particular term is going to be split into two parts. I am going to call this entire group G over KYA. This is called HTOG. This means height of an overall gas transfer unit, or in short it is known as HTU, overall gas transfer unit, height of the overall gas transfer unit. So HTU means height of the transfer unit, but since this is based on the overall gas phase coefficient, we add this extra term, overall gas transfer. Okay. So now we can write that the column height Z is equal to HTU times this integral that I have here. I am going to call that as NTU. Okay, and this integral dy by y minus y star going from y2 to y1, we will call this as NTOG. This is the number of I said I am taking this minus sign inside and I am changing the limits. So number of overall gas transfer unit, in short NTU. So in the calculation of the height of the column, we first calculate the height transfer unit HTU based on the mass transfer coefficients and interfacial area, and then we calculate the number of transfer units NTU based on the average or the driving force available for the mass transfer. Any questions so far? Now, until this, if you look at what assumptions with regard to the dilute mixture we have used the G is constant because dilute mixture, and then we have used the K type mass transfer coefficient. Okay, these are the two things. What we have not really used yet is the Henry's law. We know that Y star is the equilibrium composition, which I can find out from the Henry's law. Okay, so I'm going to show further subsequently that how to calculate this integral analytically for Henry's law type equilibrium lines. Okay, so you will get an analytical equation for NTU also. So we'll recall this Henry's law is given as Y star is equal to mx. So I can substitute Y star equal to mx, but then x is another unknown variable. So how do I get x? So NTOG is y2 to y1 dy by y minus y star, and instead of y star I can substitute mx. Now how do I deal with this? I have two variable y and x. So how can I deal this situation? Yes, very good. Yes, you are going to find the equation of the operating line, and we are going to replace x in terms of y, because we know that the operating line is something that gives the relationship between y and x. Remember, there are two lines, equilibrium line that gives a relationship between y and x, and another line that is material balance line or operating line, which also gives y versus x. So I can now use the operating line to replace x in terms of y, right? So that's exactly what I'm going to do now. So when I do mass balance, so this is my so we'll just use simply G because G is constant here. So let us do a mass balance in this particular envelope, where this is at a particular location in the column. Okay, so at this point we will call the compositions are x and y. Okay, so writing mass balance, so you'll get Gy plus Lx2 is equal to Gy2 plus Lx. Okay, this is written for countercurrent operation using the top phase composition. You can do the same thing with the lower side composition also. Okay, and then from here you can write that y is equal to L by G x plus y2 minus L by G x2. Okay, so this is the operating line that I was showing here before. Okay, the operating line I was talking about here, right? This line, that's basically that line. Okay, depends on the ratios of L by G, ratios of the mass flow rate, ratios of the flow rates. So from here you can also find the value of x. You have to just invert it. I'll just give the equation directly. You can find this out. G by Ly so now I can find this expression y minus mx, y minus m times, I can substitute for x here. So, you can see some group of terms are coming up. What do you think about this term mg by L? What does this signify? What is m? Slope of the equilibrium line. What is L by G? Huh? Slope of the operating line. So, there is a coefficient that's coming up, that is a ratio of the slope of the equilibrium line to the operating line. Okay. So, we can write this as m by L by G. Okay. So, m is the slope of equilibrium line and L by G is slope of operating line. Okay. And we are going to define this as 1 by A, or in other words A is equal to L by mg, and we are going to designate this as the absorption factor. Now, I realize that we are using this letter A for so many things, for area and so and so, but this A here we are denoting as absorption factor. Okay, it is defined as L by mg, but here we have the inverse of that, mg by L. So, y minus mx is given as y times 1 minus 1 by A plus 1 by A, or y2 by A minus mx2. So, I can now substitute that expression in this NTU or NTOG. So, my NTOG calculation is y2 to y1 dy so this basically is in the form of dy by ay plus b, something like this, and you can easily integrate this out, right, because this entire term is a constant. 1 minus a is also constant. So, it is basically in this particular form. So, if you integrate this, I will give the final expression, but you can check this yourself. So, this expression gives you the number of transfer unit, and you can see it depends on this factor A. A is the absorption factor, depends on the slope of the equilibrium line on the operating line, also depends on the composition at the inlet and outlet y1 and y2, and the inlet composition of the liquid phase. That is all. Okay. It does not depend on the mass transfer rate, it depends only on the property of the operating line and the equilibrium line, because that is what set the average driving force. But the mass transfer rate effect comes through HTU, the height transfer unit. So, therefore, the height of the column is written as the product of H2OG into NTOG. This includes the mass transfer coefficient or mass transfer rate, interfacial area, and the flow rate. All these variables enter in the calculation of height of the column through the height transfer unit, whereas the equilibrium line and operating line properties enter through the number of transfer unit term. Okay, and you have to, whenever you design this column height, you calculate the HTU and then you calculate NTU. The product of that determines the total height of the column. Like I said in the beginning, this is all possible because we have invoked the assumption of very dilute mixture. Okay, we could use the Henry's law, and we could use the constant molar flow rates. Okay, so that we can do all these things analytically. Okay. When we deal with the when we go to the concentrated mixture, all this assumption will not be possible, so we have to deal this little differently. Okay, but this is a good step. If you know the compositions are very less, you can directly use this equation. You have to know absorption factor and other things, and there you are. So there is one catch here. What if A is 1? If A is 1, what does it mean in terms of driving force? 0. Okay, 0, constant, infinity. Again, I appeal to your kind of common sense here. All you need to do is you look at the diagrammatic lines. Equilibrium line is here. If A is 1, which means the slope of the operating line and the equilibrium line are the same, isn't it? So that means you are talking about another line with the same slope. And here the driving force here will be of same value, right, across y, right. So that means in the calculation of NTOG, this y minus y star is actually a constant of y, and you can take it out. Okay, so this simply becomes 1 by y minus mx2, and you get y1 minus y2, right. And that's what the NTUG can be directly calculated from here. You don't have to use that equation that I showed. That is only for another case where the slopes are not necessarily equal. This is equilibrium line, and let's say your absorption, your operating line is something like this. Okay, this is also straight line, but you can see this driving force is not constant throughout y. It keeps changing, but you can still integrate it out if these are straight lines, which is what we have done here. So this equation allows the variable driving force, yet the two lines have to be straight line. Okay, you are lucky if both lines are parallel. You don't have to do any integral. You can just directly integrate this out. Okay. Now think about what happens if A is greater than 1 or A is less than 1. What is the consequence of that would be? Let someone else answer. What is the consequence of A being more than 1 or less than 1? What does it mean? So A is L by G by M, right? So this diagram I have shown, the slope of the operating line is more. So this would actually correspond to A is greater than 1. Oh well, let me. This slope L by G is smaller than M, so here A is less than 1. So what does it mean in terms of the driving force here and here? So here in the case of A greater than 1, the driving force is more on the bottom side, at the bottom of the tower, and then as you go up, the driving force actually becomes smaller and smaller. When A is actually less than 1, it's the opposite. There is larger driving force at the bottom of the tower, and as you go to the top, the driving force becomes small. So there are a lot of intuitive picture you can develop by looking at this graphical analysis of the operating line and equilibrium line, right? All right, so we'll stop here, and what I have done here is dilute mixture of absorber. You can do the same thing for stripping section also. Okay, so next class I will talk about stripping section. Yeah, we'll stop here.